Okay, so this is our last new topic lecture. So the way the schedule goes, we'll go through this one. Then Tuesday of next week, it's a holiday week, Thanksgiving week, so there's only a Tuesday class scheduled. But I'm going to be here on Tuesday, and it'll be sort of an open lab period. And so if you would like to work with your teams and like to ask me questions so we can debug things and try to get suggestions, whatever, then you're welcome to come to Tuesday, and I am here for that. Otherwise, no new content will be covered. I won't be taking any sort of attendance. So that's the plan for next week. Of course, Thursday, Thanksgiving holiday, so no classes. The week after that is the last week of classes. So Tuesday, we'll have a final exam review lecture. Wednesday night, your final project report and presentation are due. Thursday, stage 1 exam. And then Saturday will be when your peer reviews are due. And then the stage 2 exam happens during final exam week. So that's kind of the schedule moving forward. And I'll repeat that here at the end of this one, just as a reminder. So any questions about that? Okay. All right, so today it's kind of a slightly more advanced topic, but I want you to be exposed to these ideas that come up when we talk about dynamical systems. Randomness and chaos, and actually stochasticity, 3 words that mean different things, but a lot of people think they're the same. So I'm focusing here mainly for now on randomness and chaos. And so randomness is actually a modeling tool that we use to simplify model building, or arguably we use to simplify our perspective of the world. Chaos, on the other hand, is apparent randomness that emerges from systems that are not random. So as we'll see examples of that, this is cases where behavior over time appears to be unpredictable, but if you look at it in the right way, it's actually totally predictable based on the current state of the system. Whereas randomness is true uncertainty, where the next state of the world is sort of randomly determined. It's not completely determined by the previous state of the world, but randomness we'll see ends up being a good thing, and chaos ends up being a bad thing. So randomness, as we'll see in a second here, makes our jobs easier as modelers. Chaos makes our job harder. And like I said, these are distinct concepts. So let's get into that and see what I mean by that. So when we talk about randomness in modeling, this other term comes up, stochastic. How many people have heard the term stochastic before? Does that sound familiar? Okay, so a lot of people, especially if they're not from the modeling community, will use randomness and stochastic as synonyms, but they're not. So stochastic models are models that use randomness instead of deterministic rules. So a stochastic model is a model that uses randomness to simplify the model. Now, what do I mean by that? Well, let's drill down into where the stochastic term comes from. So stochastic is actually from the Greek term for guessing or conjecturing. So the idea here was that the first time stochastic models were published in papers, everyone before then assumed you needed a fine-grained understanding of how physical processes work. So you need a deterministic laws like Newton's law that sort of said, if you know the current, where every particle is, and you know where, what velocity all the particles are going, what their accelerations are, you can figure out where the particles will be immediately after that. And that's so everything is sort of determined by the state of the world right now. But that's so complex when you have large numbers of entities in your systems that it becomes kind of unbearable to put all of that detail into a model. And so the modelers that first came up with the idea of stochastic modeling said, we can't just arbitrarily add randomness. People will say, are you saying that the nature is fundamentally random? And that's not what we're saying. They said, so we need a new word for it. So we're going to make a conjecture or a guess that we can approximate the world as if it was random. And by doing so, the variation that actually is not random can be explained or generated without having to deal with all of the minor details that actually go into that variation. So it's a conjecture that behavior of a system is fundamentally random, even when it may not be. So we're just going out there and say, it's just going to simplify it. Like a student, could be late to class, or I could be late to class, and could walk in that door at any moment. And I could, in order for me to figure out when a student is walking through that door, I would need to know so much about everything else that's going on, probably within miles of this, like what every single person is doing at every single house, and what's going on at ASU, and if there's traffic and all these different things. So I could deal with all that, and that would give me a deterministic viewpoint of whoever's going to walk through the door and win. Or I could say, you know what, on average, this number of people walk through the door at this particular rate, and it fluctuates around that rate. But generally, most of the students are going to be here by a particular time, and maybe there'll be a few more that are a little bit after that. So it's as if they're being generated randomly, but they're not really being generated randomly, but the statistics will be equivalent. That's what stochastic modeling is substituting randomness to make the job easier. So this reduces our modeling burden, and I'll give some better examples of this that link to things we've already done in this class, but it's going to make it easier to achieve boundary accuracy and structural accuracy, because we won't have to put as many things in our model, because we're going to get a lot of the variation for free from the randomness. So let's see, to get a better idea of what I mean, let's go back to the bacterial growth model. So if you remember going back to lectures D1 and D2, we're trying to model a population of bacteria growing on a plate or growing anywhere. And we know that one bacterium, on average, if you wait one birth event, one reproduction event every W time unit. So on average, if you wait W and you're focusing on one bacteria, after that W, you'll see 2 bacteria. And so the way we handled that, modeling that, is we said, well, we know that in reality here, you get a reproduction event, and then maybe less than W time, another reproduction event, less than W time for that, another reproduction event, but then maybe more than W time, another reproduction event. So you get true variation around the average. But for our purposes, we kind of turned it into an averaging process where we said, well, let's forget about all that variation, and let's just say on average what happens. And on average, we know an average one event every W time units. And so in our models that we've learned so far, we said, well, let's just assume every bacteria is pouring out at this kind of flow rate of 1 divided by W. And then that way, after W time units, you get another full bacteria accumulates in this sort of accumulator of bacteria. And we're going to do that. We're going to see how much a bacteria has accumulated every DT time steps. And after that DT time steps, anything that's accumulated in the previous step is going to start pouring out itself. And that's how we approximated this process. And so, we've seen this graph over and over again. We have this stock of bacteria, and it generates this flow up here. We have this DT set in our simulation. It takes all the flows, it scales them by DT to figure out how much bacteria will be added in this interval, and then it adds it. So in the next interval, our stock is expanded, and now our new expanded stock starts flowing out, and the same thing happens over and over again. And so this process goes on, but it's modeling the average behavior of the population. And so this is saying if I had 100 Petri dishes and I counted how many bacteria were at any instant of time, and I took the average of that, and then I did that again for another instant of time, another average, and then another average, across the 100, the average behavior would follow this trajectory right here. So it's assuming that the population 1 DT later can be predicted perfectly from the average population now. So it's a trend. So in any one Petri dish, it could be varying. You could be growing faster than this. You could maybe be going slower than this. Sometimes faster, sometimes slower. But if we average across all 100 of them and watch the averages over time, it follows this pattern here. Now, we might want to capture all of that true variability. So how do we do that in a simulation? How do we make it so that every time I run a sim, it's like another Petri dish? Like, again, if I set down 100 Petri dishes on a lab bench, and I look at that and I start them all at the same time, some are going to grow a little bit faster than others. And it's like, I know that I've got an average trend, but I know that I want a little bit of variability to be able to say, okay, so this Petri dish is slightly different than this one, is slightly different than this one. So I can then see like the variability, like not just on average what things do, but what's the worst growth rate I can get? What's the best growth rate I can get? How do I get that type of variability into my computer? So every time I hit run, it's like generating a new Petri dish. That's what I'd like to generate. So if I wanted to do that in my simulation right now, if I take the endogenous perspective, I have to sort of think about what are all of the things that I need to generate the true variability. Like, this bacterium happened to be reproduced faster than average, but if I went back, this bacterium reproduced kind of slower than average, or maybe I got it back, maybe it's this one that reproduces slower than average, or however we divide these up. But some of these bacteria are slower than average, some are faster than average. Well, if I had asked myself, if I want to build a true deterministic model of all the mechanics that go on inside a bacteria, how do I account for this variation? Or if you ask a cellular biologist, why do some bacteria reproduce faster than others? And they will give you all sorts of, they'll say, well, maybe there's, more, maybe they're more of a particular cellular component inside. Maybe some cells have more mitochondria than others. And so, well, that wouldn't be the case for bacteria, but maybe there's certain, certain fuel that they need to effectively reproduce that some have more of and others have others. And so that's going to limit their growth rate. Or maybe some of them have more access to nutrients and other ones don't. And so I ended up having to account for all of these things inside the bacteria, as well as all the things outside of the bacteria, to try to figure out what's causing this bacteria to reproduce at a different rate than the previous bacteria. And then after it reproduces, its state might change, and then it might reproduce slower the next time around. So there's just like a lot that I would have to build into my model. I go from having a 4 stock model to having like a 4,000 stock model that's kind of come up with all of the stocks and flows just inside one particular cell. And then to do that again over all of the cells that I'm trying to generate, it becomes too much. There's just too many variables for us to deal with and too many to calibrate. There's no way we're going to actually be able to measure that, like get a population of 1,000 and get, every bacteria and all of the right variations. We just can't do it. So instead, what we think about is, if you really think about it, I can look at the time in between reproduction events and they follow some distribution. So it's like if I'm playing a board game, I could say if I'm this bacteria in the board game, am I going to reproduce quick or slow? So do I have to wait a long time or a short time before I get to do another reproduction event? And if I was doing it on a board game, I would roll a die, maybe a 20-sided die, and I would look on a card and it would say, if you roll between these numbers, you get to reproduce. If you didn't, then you don't get to reproduce. And if I set up that card the right way, maybe I could actually generate the same pattern I have here. So maybe if I, set it up so that a 6 meant a particular reproduction, a 2 meant another, a 5 meant another, and so on. If I set up the right mapping between my 6-sided die or my 20-sided die and these times between reproductions, if I just keep rolling die, maybe I can mimic the stats of real bacteria without having to actually do all of the things that real bacteria do to generate their real variation. That's what stochastic modeling is replacing the details with randomness, because in the end, the outcomes may not look that different. If I think about a random probability distribution, like a normal distribution generates a huge amount of variability. All you're needing to know is the mean and the variance. So with 2 numbers, I can generate sometimes it'll be very large, sometimes it'll be small. So I can I can keep drawing. Like if I went to say that the reproduction time has an average time of W with a variance of 2 time units or whatever, then every time I want to do a reproduction event, I can just draw from a random distribution that has that mean and that variance. And then that will give me a short reproduction sometimes, a long reproduction other times, and so on. The same way rolling a die at a board game sometimes gives you a 1, sometimes gives you a 6. So stochastic here, it's our approach. It describes a model, not a real phenomenon. It is stochasticity, or this modeling approach, accounts for the omitted degrees of freedom in a model. So what I mean by that is all of the details left out, we replace with randomness. And so normally we might have to account for 100 variables, but if we put in some randomness, we might be able to bring them down to only like 2 parameters of a distribution, like mean and variance. And we forget about all those other details. And it makes our models more generalizable, stronger, and just easier to interpret and understand. That's what we mean by stochastic modeling. So before I kind of go on to say, the details of how we do that, are there questions about this general idea? Turning our rules into board games. Yeah. Mm-hmm. So the question was, do people actually build super detailed, high-dimensional models of things like bacteria? And they do. They're a lot of times in biomedicine, we refer to as so instead of just calling simulations, they actually call them in silico models, like in vitro, but instead of vitro, it's silico for silicon. So it's a little, but the idea there is, in that case, let's say you're investigating the way a drug interacts with a particular bacteria. So you have an antibiotic, and it attacks the particular bacteria. In that case, before you maybe go on to laboratory trials, if you happen to have a cell biologist who knows how a bacterium structured, like to a high amount of detail, you might actually simulate that really high dimensional bacterium in all of its glory. You probably only simulate one at a time. But then you could say, imagine my simulated bacteria. I'm now going to have a simulated drug come in and see what happens as it comes through the cell wall and incorporates into that. And that'll give me an idea of what might happen with the real bacteria. You probably wouldn't simulate a colony of them to see how they form bacterial biofilms and things like that, but one at a time. Yeah, that's like these in silico models. Right now, there's a really popular thing in simulation called digital twins. And so we've reached enough computing power that twins, like me and another me. And the idea would be that if let's say I am running a factory, I can create a very complex factory, manufacturing system or whatever. I can build a high fidelity model that, like it looks like I'm watching like a 3D, virtual world. It's like meta, like a metaverse version of my factory that constantly is getting data from the real system to recalibrate. So as this high dimensional model, like if I just let it go, it would drift away from the real system because it's not ever going to be perfect. So it runs itself for a second or whatever, and then it takes a bunch of data over the factory, and then it syncs up the simulation model, bringing it back to the factory again, and does that over and over and over again. And what they do with these digital twins is then they can say, oh, we noticed there's something weird going on in this part of the factory. We would like to experiment with a particular change in our digital version first before we actually go out and retask people on the floor. So that in real time, you go out and you screw with your digital factory to see if the digital twin does what you think it's going to do. And if it does, then you go back to the real system and you can say, okay, the thing that I just tried in the digital version, I'm going to try in the real version. And so digital twins are meant to be extremely high fidelity, but the downside of them is not only do they take a lot of computational power to do in real time, but they constantly need calibration. Because once you get to that level of detail, like all models are wrong, some are useful. The only way a digital twin is useful is if you're constantly correcting for its wrongness. Because like the only value a digital twin has no generalizability. It only works in that it is a mimic of the real system, and it will only accurately mimic for a short time period. And that's why it has to constantly be resunk back to the real system. So yeah, the modeling spectrum is kind of full of this stuff, but but you don't always need to add all that detail in, especially when you're studying like large scale systems. Any other questions about this general idea? All right. All right, so let's then see how do we actually do this inside computers. Computers, which by the way, are not random. So I mentioned for a board game, you can have a 20-sided die. And like, let's say you have six possible outcomes at a particular step in a board game. Well, if you want to bias it so one outcome's more common than another, then you can't do that with a six-sided die because all six sides come out with 1/6 probability. So instead, you go to a die with more sides, like a 20-sided die, and then you've got a little card that says, for this spot on the board, if you hit a 1 through 10, then outcome 1. Otherwise, all the other pairs here, outcomes 2, 3, 4, 5, and 6. And the idea here is that 50% of the time you'll get outcome 1, but then the other, 50 divided by 4, so just 12.5% or whatever, you end up getting, I guess I didn't do that right. Well, anyways, you can do the math, but the other 50% is then spread out over these 5 here. So I guess 10%, right? So 50% I get outcome 1, 10% 2, 10% 3, 10% 4, 10% 5, 10% 6. So each one of the 20 sides comes out with a uniform probability, 1 out of 20 probability. But this little translation card makes me generate a loaded die that comes out with 6 or half of the time one shows only one of its sides. So if I have a high resolution source of randomness like a 20-sided die, this becomes a programming tool where I can now shape my randomness to look like something else. And so I can create these unfair objects that hopefully are shaped to look like reality. And I can do that with a coin toss as well, or a probability of some event. So if I want to say that a coin comes up heads, with 15 out of 20 times, so I guess 75% of the time, then I just say that if I roll a 1 through 15, let's call it a heads, otherwise call it a tails. And again, it doesn't have to be a coin toss that I'm mimicking here. This could be the probability of some event, like you happen to hit the spot where you have to fight a dragon. Well, you lose with the dragon 75% of the time, you win 25% of the time. I don't have to actually, in the board game, say all the details of however the heck you tried to approach this dragon. I just said, however you do it, I don't know whether you use a sword or whatever. I just know the stats on a dragon are pretty tough. They're going to win 75% of the time. I don't know how, but they will win 75% of the time. So that's what I mean. It reduces the modeling burden. So now I just have to simulate 75% of the time the dragon wins. So that's what we're doing inside the sim. Now, where do I get this randomness? So in a board game, I have a die that somebody can roll, and that's how I get the high resolution randomness. I don't have that in a computer. Some fancy computers can do things like sampling the temperature, sampling molecular activity, those sorts of things. But in general, the average computer, like the one sitting next to me, doesn't have a true source of randomness. But what it does have are these functions that if you give them a starting number, they'll give you a string, a deterministic string. So every time you start with that number, it'll give you the same string out. But it's very difficult to predict what the next number is going to be. And so they act like die rolls that are just super repeatable. So inside a computer, there's a bunch of these strings, so I'll call them streams. In this case, let's say index 0, 1, 2, 3, 4, and 5, or 0, 1, 2, 3, and 4. And so it's kind of like I can ask the computer, use stream 0 to roll the next number from the sequence, and it will give me another sequence. Then I can say, all right, that's stream 0, give me the next number. Now, if I run my simulation and ask for stream 0 again, the simulation will be identical to the previous time I ran it. Because it's like having a die that while you're using it, it gives you apparently random numbers. But if you put the game away and come back, it's like you'll play the exact same game again, so long as you're using the same die. So it's almost like you have a board game up on the wall, and every time you use the die, if you want to play the game again, you got to throw the die away and get a new die, or else it'll be the same game all over again. So that's what the computers have got in them in order to simulate randomness. And so if I want to generate 100 Petri dishes in simulation, I need 100 of these die, which turns out the computer's got as many of these as you want. And so Petri dish 1 would be random stream 0, Petri dish 2 would be random stream 1, and so on. So for two simulations to have different outcomes, you have to use different streams, just like for two board games to have different outcomes. In this bizarro world of the computer, you need two die rolls. And so does that make sense? I mean, it's a little abstract, but I don't want to go into all the numerical methods behind approximating randomness. But this is kind of the best conceptual model that I have for it, is that inside the computer, there are mathematical functions that are indexed by numbers, which we call seeds. And whenever you give it a seed, it gives you a sequence of nearly, millions of numbers that look random. But if you restart that sequence over again, it'll always give you the same sequence. That's why we have to generate new seeds to generate apparently new sequences. That's what's going on inside the computer. Questions about that? Does that make sense? All right, so what do we do to make use of that? Well, I can go into, so this is the standard way we do it. So this is, imagine a population of bacteria. This is really a boring one, whereas no birth rate, it's only the death rate. So I initialize this with like 1,000 bacteria, and I have this deterministic deaths formula. This is the normal formula, no randomness yet, the things we've already done, where I've got an average lifetime. So I put in this flow, deterministic deaths equal, what would does anybody remember, what would the formula be if I wanted just a standard kind of death process with an average lifetime here? Does anybody remember? We've done this one over and over again. Same with this, like the bacterial model. I don't know. Let's see if there's other ideas around here. Do you also kind of hesitant to which one divided by which one? Yeah, that's what I'm looking for. So remember the units here are in whatever population units are, like bacteria. Flows are always in this unit divided by time. So the only way I can get, if I have this as an input to the flow, and this is an input to the flow, the only way I get the deaths formula to be the right units is if I do population divided by lifetime, because then I get the right units. So that's my deterministic deaths flow. Everybody get that? Is there any questions about that? Kind of fundamental to make sure we're all there before the final exam for sure. All right, so if I do that and I hit play or run or whatever, if I start with an initial condition in this population of 1,000, and I hit go in Vensim or Insight Maker, I get this nice smooth decay. And so again, this is not saying that every Petri dish population will look this way. This means that on average, the average across the Petri dishes, if I look at them all, like 100 now, 100 a little later, 100 a little later, the average across those 100 will look like this. Well, how do I generate variation that looks like each individual Petri dish? That's what I really want. So I want to capture that variability. So that's what I'm going to try to add to this. So what I'm going to do is I created a new model that I'm calling my stochastic population model. And so I've got a little stochastic population here, and I've got a deaths outflow, a stochastic deaths outflow. It's got average lifetime going in just like before. It's got the population going in just like before. But now I've inserted that random stream. This is just going to be that seed, that number, like 0 to 4. So it's just going to be a number in here which tells the computer which die roll to use to generate every time you run the sim. And then I have to put the time step into here too. So this is your DT. So it turns out that I need to also tell it how quickly the thing's running. So that's like an artifact of how we have to do this. And so let's see what the formula is. So let's try to build that formula up. So without worrying about the formula just quite yet, let's try to again sort of think about what's happening here. Imagine I have these, I don't know, 10 maybe, 1, 2, 4, 5, 6, 7, 8, I don't know, 9 or 10 bacteria currently in this population, say initially. At the next time step, I need to ask how many of them survive, or another way of saying that is which ones die. So which one of these bacteria will survive to the next time step, the next DT? That's what I need to sort of ask. So I'm not generating a continuous flow of bacteria. I'm actually saying not like 0.1 bacteria on average died this time step. I'm going to say no, exactly 2 bacteria died on this time step. So I basically need to flip a weighted coin. It's kind of like in Gladiator or whatever. It's like the emperor going thumbs up or thumbs down on each bacteria, deciding which one gets to survive the next time step and which one doesn't, based on a probability that's related to their average lifetime. So I'm going to show you how to write that probability, but let's assume that we figured that out. So the probability here, so actually I've got it right here. So I've just said the time step divided by the average lifetime. This is our probability of a death, basically. And so the idea here is, if you sort of think about it, on average, if you wait average lifetime, a bacteria should die. So, on average, sort of the probability of death after average lifetime should be 100%. And so if we cut that down and say, well, what if I'm only waiting what if a time step is half a lifetime? Well, then it should be roughly 50%. What if the time step is a tenth of a lifetime? Well, then it should be roughly 10%. And that's what this sort of is saying here. So this is DT divided by average lifetime. That's the probability. So basically, for all of these bacteria, I have this weighted coin. It comes up heads this often, time step divided by average lifetime. And with that, I can get that these ones with the thumbs up, they all got tails. These ones with the thumbs down, they got heads. And so they're going to be removed from the population. So an actual integer or whole number is going to be removed from the population, not a fraction. Question? Yes, yeah. It's like I flipped a weighted coin for each one of them. So for you, I flip a coin, I see that come heads or tails. And so this one, tails. I flip it again, heads. Tails, 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 heads, heads, tails, heads. Other questions? Okay, so I subtract these 4 out of my population, so I'm only left with those 5. So exactly a whole number of bacteria exist at every DT, never a fraction. So I'm simulating the real variability in our system. It looks much more realistic. So how do I implement this formula? So this is going to be a specific case for this here, but then I'm going to show you a generic case that you can use for any deterministic model you've already built if you wanted to add this type of variation. So for this particular case, this is one way to do it. You can do the way that I'm about to show you for generic, but this is just for this purpose to kind of map to this narrative here. In Vensim or Insight Maker, there is a function that generates what's called an outcome from a binomial distribution, a random outcome from a so-called binomial distribution. And basically, it tells us that if you flip a coin a certain number of times, and you know what probability that coin comes up heads, it will then give you, there'll be a distribution of how many times it'll come up heads, and it draws from that distribution accordingly. So this random binomial function here, and I'm going to plug in these numbers, but this is it generically here, is that it allows us to first put in our random stream. So that way, if we run it with 0, we'll always get the same outcome. We run it with 1, we'll always get a different outcome, but it'll be the same with 1, 2, 3. So it allows us to generate different outcomes as long as we change the random number stream. And then it has time steps. So this is a weird thing that I need to convert a number of deaths into a deaths per unit time. And since I know I only moved 1 time step forward, it's going to be this number of deaths divided by time steps. So it's just something I have to put in there because this is a flow formula, and flows always have to have the units of population per unit time. So then, like I said, random stream. These operators are advanced, and I don't worry about them in this class, but basically one of them is always 0 and one of them is always 1. The number of tosses, this is going to be our population. So how many times do we flip that coin? The probability that each coin comes up heads, which represents a death. And then we can actually tune, so that's just my time step divided by average lifetime. And then we can tune whether or not we want to constrain these outcomes so that they don't go above a certain amount or below. We're going to just make this 0 for the minimum, and the max is going to be our population size. So if we put all that together, I get this ugly thing here, which this will, every time it's run, it like rolls a die that is going to give me an output, which is going to tell me how many bacteria died that time step. And so then I can take this formula, put it into the flow here, and I can do this for Insight Maker as well, something really similar to this. And what do I get out? Well, I'm going to zoom in here, but the blue line, that's our smooth flow. And the red line here, which you can kind of see is coming away from the blue, that's going to be our stochastic flow. And if I zoom in here, I can see that there is a distance between them. And notice that the red one, it all has these little steps. So it holds on to a certain population until it drops one. And so basically, it's always going to be, whole numbers. And we're pretty much only going to lose one bacteria at a time. Occasionally, we might get a rare event where we lose several, like maybe I lost 2 here. But aside, I mean, this is just diagonal because of how it's plotted. But the point is here, the population, it never exists in between whole numbers. Just like a real population, there's never a fractional bacteria. And on top of that, if I go and I change my random stream and I rerun this model using stream 0, 1, 2, 3, I can generate data sets for each one of these random streams. And it gives me, every time I use a different stream, I get a slightly different output. So if I zoom in on this, I see the blue one, that's my deterministic one, like we've been doing all semester. But the green, red, gray, and black ones, those are this stochastic model run starting with different random streams. So this is like Petri dish 0, Petri dish 1, Petri dish 2, Petri dish 3. So we can see that some Petri dishes are kind of a little better than average, some below average, but if I were to average across the Petri dishes, then I would recover the average behavior. So it gives me an idea of how much variation I'm going to get across my Petri dishes, but it's still consistent with the average trends that I see in my deterministic model. So any questions about this perspective here, these stochastic simulation outcomes? Yeah. Okay. Okay. That's the index of die. So, so that is this variable here, which is a constant. And if you drill down into this constant, it could be 0, 1, 2, 3. It could be whatever you want, as long as it's a whole number or an integer. Mm-hmm. Well, I'm going to show you the generic version where if you had any one of these flows, you could pop it in. This one just works really well for a population case because we already know like how many times we need to flip a coin. It's how many individuals are in the population. Each one of them gets a coin flipped. But I'm going to show you something that's more generic in just a second. But yeah, basically the generic thing is something like this. Like we can turn any flow into like a probability that something's going to happen. And it's going to look a little bit like this, but it's a little harder to justify it being referred to as a binomial. But so that's what I'll show you the kind of generic version, which also would work for this version. But because this is so appealing in that like it's like 9 bacteria, so that's 9 coin flips, it just made sense to use the binomial for this. It's the different die you're using. Yeah, that's a good question. So it's like those 100 Petri dishes. No one is right. So if I'm running an experiment, I need to usually generate, like, let's say I did have an antibiotic, I was testing on bacteria. I would not run that on 1 Petri dish. I would run it on at least, say, 10 Petri dishes. And I would see what is my survival rate in each one of these 10. Because it could be that one bacterium line is just really lucky and it's going to escape, or one's just really poor and it's going to die. And so if I only ran one, then that's not going to be enough for me to say the drug works. So in order, in a real laboratory, like an ISTB1 over there, then if I would have to sort of average across these and then do something like from statistics, like a t-test or a survival analysis or one of these statistical tests to say, across these 10, do I have evidence that my drug is working compared to the 10 where it wasn't working? You do the same thing here. You actually need to run independent replications of your simulation. So let's say you have a simulation and you want to say, I implemented some fancy new way to deal with garbage in a simulated city. Well, you might need to run 50 replications, so 50 different random streams without the garbage mechanism, and then 50 random streams with the garbage mechanism. And then across both of those, you need to do a statistical test, like a 2-sample t-test that would sort of say, is my population without garbage different in average than my population with garbage? So that's the, and I'll mention this, that's the downside of stochastic modeling, is in order for us to reason about it, we actually have to run multiple replications. So up until this point in the average behavior, you ran your sim once, and then you might make a change, but then you run it once again. Now, because we have variation every time we run the sim, we have to run the sims, a single simulation model, multiple times. In other words, with multiple streams, and then average across those. A question online. If you subtract from the possible deaths, won't that skew the death rate low? How do you allow the death rate occasionally to be higher than the average death rate? So the question here is let me just say the death rate is not higher than the average death rate. In the stochastic model, the death rate is still equal. The average death rate in both of these are the same. So they both actually got to start out here. But what happens here is that some of these just happen to get lucky for a couple of runs. And so that kind of lifts them off of the average over time. And so this one here that's higher, it actually isn't dying at any lower rate. It just happened to have a couple of longer plateaus. Like notice this gray one, it has a plateau here. So just by random chance, this gray one doesn't have any death for this period of time. But notice that all of 4 of these, and including the average, are pretty much parallel. So if I was to do a so-called survival analysis on this, which a survival analysis is a statistical method to compare death rates when there is randomness, then all 4 or 5 of these, if I include the blue, would actually end up having the same survival rate. They'd have the same death rate. It just so happens that this one happened to hold out a little bit longer initially before its first death. This one didn't hold out quite as long for its first death, and so on. Notice this one's got a really sharp drop, so here it was lucky, here it was unlucky, but on average, all 4 of these sort of look like the blue line. So it's not that any one population manages to get less of a death rate than the others. It's just that at small time scales, some bacteria are lucky. So on average, you might die if you drive like an idiot. But there's a lot of people drive like an idiot and don't die. So you're changing the average, but just driving like an idiot doesn't guarantee that you're going to die. You might kill somebody else and you won't die, or something like that. So that's the point, is that like we can't account for the difference between this petri dish, and so on. But we know that across all petri dishes, there's going to be a little variation. Across all idiot drivers, some are going to get away with it and some won't. And so this one happens to get away with it. This one maybe doesn't. But that doesn't mean that this one is fundamentally different than this one. This one's just a little luckier than this one. Hope that makes sense. Any other questions about this? Okay. All right, so captures realistic variability in simulation studies without actually having to put the real sources of that variability in. It's more realistic, but as I was just saying, you actually have to run more simulations to understand the general trends. All right, so how do we do this more generically? Well, if I have any flow rate, there is a formula that I can give you here. And so so before I have this probability formula, I can generalize it to this probability formula, which says the probability basically of an event, the probability of a single death in this case, is basically the time step times the flow rate. So remember, it was time step divided by average lifetime. Well, generically, it's time step times the flow rate. So the flow rate is the average amount of this flow event, whatever this is, how much it happens over time. So this sort of saying, well, if we do to take that flow rate and multiply by the time step, if the time step is small, that actually gives us the probability that every time step we're going to get a flow event to happen. So what we do in Vensim or Insight Maker is we can implement this ugly flow equation instead, which allows us to do a little bit more generic things, just to translate any deterministic flow into a stochastic flow. And it basically turns that random binomial into this if then else statement, where the first thing before the comma is a condition. And if that condition is true, then one event happens. If that condition is false, 0 events happen. And so the condition here is it draws a random number between 0 and 1. That random number will be a real number between 0 and 1. It could be 0.4267, whatever. That basically is the computer's version of a 20-sided die. But now it's like a continuum-sided die. It can give you a whole zillion lots of numbers. And then you can say, if it's less than or equal to any probability, this event happens. Like if you draw a random number uniformly from between 0 and 1, and you compare it to any number, the probability that the thing that you drew is less than what you're comparing it to will be equal to what you're comparing it to. So this allows us to basically say we're going to get a 1 out of this if statement with this probability right here. And so anytime, if you wanted to make your simulations more variable, anytime you had any flows, you just go into here, into your flow formula, bring a random stream into it so that you can adjust these numbers so that you can run it every replication with a new random stream, and take whatever formula that you had in there and copy it, or cut it out, and then write this thing in. And instead of flow rate, put parentheses and then paste your flow rate in, and then it'll work the same way. But then when you simulate it, you'll actually get variability. So this is the sort of generic way to implement stochasticity in our system dynamics models. There are other modeling frameworks. They're called discrete event system simulation tools that this is much cleaner in. Vensim is fundamentally a system dynamics modeling tool. That's why this looks so ugly. If you do this a lot, don't use Vensim. There are other tools like Arena or even Visio, I think now allows you to do this without these ugly formulas. And those tools are made so they're primarily or only stochastic. So they cut out all the rest of this junk, so you can basically just give it probabilities. But I just want to give you an idea that this exists. All right, so any questions about that? Yeah. Mm-hmm. Yeah, so you have to supply in this random uniform not only the minimum and the maximum, but also the random stream. So if I draw 100 numbers and this random stream is 0, it will, let's say if my simulation draws 100 numbers and I rerun my simulation, if I didn't change this random stream, it'll generate the same 100 numbers again. So it might be 0.2, 0.6, 0.7, 0.1, whatever that sequence is. If I rerun my sim, if I didn't change this random stream, it'll be the same sequence of numbers again. So changing the random stream from a 0 to a 1 guarantees that the next random numbers, instead of being 0.2, 0.7, 0.6, 0.1, it'll be maybe 0.47, 0.5, 0.1, 0.2. So it basically says, it's like changing the random stream from a 0 to a 1 to a 2. It's like going to the shelf and grabbing a new die So when you roll that die, you'll get a different sequence out. And once you're done with that die, you can put it aside and grab a new die. And that's like changing this one from a 0 to a 1 and rolling it, and you'll get a new sequence of numbers. Yes, so it's going to draw a uniformly distributed number, real number, between 0 and 1. So if I change this to 0 and 10, it would draw any number between 0 and 10. No, the random streams specify, that's like an extra argument here. So it's the random stream is just what I'm using as my index for the die. This is like the 20-sided die, and this is like the ID of the die. Like it's like saying this is the red die. So imagine this is a random uniform 0, 1 red, and I could do random uniform 0, 1 purple, and that would be the purple die. So it just gives us an ID of the die, but all of the die give me numbers uniformly distributed between 0 and 1. Right. That's right. Any other questions about this? You're not going to need to know any of this in more detail. All I want you to know coming out of this is that you can use randomness in our simulation tools to actually generate variability without adding a whole lot of new structure or variables to your models. So you can have models that look fundamentally the same as the existing models we have, but generate variability, and you can tune that variability as well. But that's a little bit more advanced. But the idea here is the models didn't really get that much more complex. The boundaries of the models didn't really change much. The structure of the models didn't really change. But suddenly we get variability out, which makes them much more realistic. Okay. Any other questions? Okay, so the last couple of minutes here, I want to then contrast that with something called chaos, because coming out of a dynamical systems course, we want to make sure we know the difference between randomness and chaos, because these terms come up a lot. And chaos, a lot of people think of it as like, oh, things are random, they're chaotic. That's not actually what chaos means. Chaos is a property of a model or a system that makes it extremely sensitive to changes in its initial conditions. Let's see what I mean by that. So here's our fishery model, our favorite model of the semester. And so we can start this model with different initial fish stock. So we can say, we'll start the model with, I don't know, 100 fish, 150 fish, or 200 fish, or whatever these three are. And regardless of how I start this model, how many fish start in it, the transients look maybe a little different, but they all come to the same point. They all reach carrying capacity. So I have different initial conditions, but they all reach the same point. They're attracted to the same steady state outcome. The long run behavior is insensitive to initial conditions. If I were to look at these models at this point, after 38 simulated seconds, and you didn't show me anything before then, I can't tell the difference between these three, or among these three models. They all look the same. So there's no sensitivity. This is not a chaotic system. No sensitivity to initial conditions. Now, I can change that a little bit. This is an example system called the Mackey glass system. So this is meant to be kind of a mathematical example, but we could imagine physical systems that will be modeled this way. And I'm not expecting you to memorize this or whatever, but I'm just showing you that this is a simple system with one stock, an inflow and an outflow. And the outflow, there's feedback there. The inflow, there's feedback here. But the feedback on the inflow path here involves a delayed version of the stock. And so if I were to look at the inflow formula, it would be this thing. And the outflow formula would be this thing, gamma x. And so there's this gamma x here, which I can take equal to 1. So this would just be x on the outflow. And on the inflow, it would be this formula here. I think maybe on the next slide, I've put it all together. So this is saying on the outflow, there would be x, and on the inflow, there would be this formula, which has a delayed version. This has a fixed delay. So this xt minus 2, that just means that it's a version of x 2 seconds in the past. It's a fixed delay version of x. So if I implement this formula here, as the inflow and this formula as the outflow, and I run this thing, this looks like a pretty simple model. But if I run this thing, then I get this output from Vensim. So I started this from 3 different initial conditions, and I get 3 trajectories that never come together. I can zoom in on the beginning here, and it's actually, they get farther apart over time. So they all start kind of close together. But even though they started closer together, over time, the blue, red, and green lines get kind of separate, and they don't even like look like the same pattern. So I think I can even zoom out later, far later, and they never get closer together, and they start taking on, like, the green one kind of like, you know, goes down here and then up, and it gets higher than the rest. The blue, I mean, they all look different. So at this point, even at large times in the future, I can somehow see the initial conditions, even though at the start, the initial conditions were hardly any different. This is just like, how many people have seen Jurassic Park, the original, the first one, you know? And so, you know, Ian Malcolm, he's sort of flirting with Ellie, I guess, and is trying to explain chaos to her. And he says, you know, hold out your hand, and he drips some water on her hand, and the first drop goes in one direction, and the second drop goes in another direction. And what he's trying to say is, wherever the water hits, you'd think it's going to go in the same direction because it hit roughly the same place on her hand, but it goes a different place. So it's extremely sensitive to tiny little variations in where it hits on her hand. That's what's going on here. That's chaos, extreme sensitivity to initial conditions. And these patterns look random, but there ain't no randomness in this. There's no, this is all just deterministic stuff. This is exactly the type of formula that we've been building throughout the entire semester, and it gets this really ugly behavior. So what we learn from that is that, well, we remember that negative feedback with delay can generate oscillations. So we know that delay can be kind of an interesting thing. Well, we can actually sort of, you know, extend that lesson to say, if we make that feedback nonlinear, so this is a nonlinear expression of the previous states, and add delay, we can generate chaos. That's one way to get chaos. So a real simple system looks random, but it's actually totally deterministic. So that's the one thing we can get. That's one way to get extreme sensitivity to initial conditions. But I also want to show you another way we can get without delay. But any questions about this general model or about this general idea? Extreme sensitivity to initial conditions is chaos, or a chaotic system. It's not random. It looks random, but there's no randomness here. There's no drawing, you know, you're not rolling any dice. If I set the initial conditions exactly here, it would give me exactly the same results again. So it is totally determined by the initial conditions, but slight changes in initial conditions generate the different outputs. Okay, so is delay necessary for chaos? Turns out it's not. This is another famous chaotic system called the Lorentz system. 3 stocks, X, Y, and Z, got inflows coming into them. This is the general form of the Lorentz system, but if I plug in all these variables, this doesn't really look that, that different than something that we've built or that you're building for your final projects. So this X stock inflow, it takes X in, the flow takes X in and Y in, and it's got this pretty simple formula, 10 times Y minus X. Or you can think of it as the inflow is 10Y, and if you want to do an outflow, it could be 10X. So all of these formulas you could implement in these flows. And it's not that complex of a system. These expressions, there's nothing too fancy here except maybe the X times the Y, or this X times the Z. But overall, there's not really that much exciting going on. But when I simulate this thing, I got 3 initial conditions, all very close together, but not quite the same. And in Vensim, I'm plotting X down here for those 3 conditions, Y up here for those 3 conditions, Z here for those 3 conditions. And not only X, Y, and Z look kind of different from each other, they're all doing different things. And all 3 of the initial conditions generate very different trajectories in all of these cases. So it's a chaotic system without any delay. So if there, and the lesson here is if you have at least 3 stocks without delay, you can get chaos. 2 stocks, no delay, can't get chaos. 3 stocks, even without delay, you can get chaos. And so now, if I look at it like I said, so this here looks like it has maybe some structure, but it just like it looks really random. Like suddenly out of nowhere, it'll do these weird things and then it'll stop doing the weird things. And like it looks random, right? So, but it's not random. And but it actually is patterned. And we can, if we know a different way to plot these systems, we can actually take a system that's chaotic, apparently random, and if we plot it right, we can re-extract the structure in the system. And what I can do, and I can even do this in Vensim, is that there's a special way in Vensim where instead of plotting over time, I can plot 2 variables together and kind of the time, it becomes what's called a parametric plot. If you remember, and maybe sometimes you go over this in like high school algebra 3 or something like that. And so what I've got here is I plotted X and Y. So X is on the X-axis, Y is on the Y-axis, and every point represents an X, a Y together at a single time. And so as time moves around, then you're sort of navigating this shape. And this is for one initial condition, and this is for another initial condition. And the beauty here is that although over time, these systems look totally different as you change initial conditions, when I plot the variables together, I can see that the structure between X and Y is the same, regardless of where I start them. I get roughly the same shape here as I get there. And I can animate that in 3 dimensions. So this is the Lorenz attractor, the so-called Lorenz attractor here, and it's going to rotate here in a second, where it's got X, Y, and so it's showing you all 3 planes. So Z versus Y and X versus Y. And so if I plot it the right way, then I can see that this system, although if I plot it over time, looks random. When I plot how the variables relate to each other, they sit on this manifold, on this so-called strange attractor. So in the fisheries model, carrying capacity is like a non-strange attractor. That's just your normal attractor, no stranger danger there. This is a strange attractor in that regardless of where the initial conditions are, they end up kind of getting stuck on this weird shape. And if I plot one of these variables over time, it's not going to make any sense. But if I plot the variables against each other, it reveals this. So one of the ways we can detect in a data set from the real world, is it really random data or is there structure there, is by doing tricks like this, plotting things against each other. And that might end up finding that, aha, even though X looks random and Y looks random, we plot them together, we see that they're related. And if I know X and Y together, I can sort of predict what the next X and Y is going to be. So that's what we talk about as a strange attractor. So this is a clear endogenous pattern that becomes clear when we observe all the variables simultaneously. Lorenz attractor. So if I were to infer that the apparent randomness measurement in X alone is noise, that would be a mistake. All right, so Lorenz themselves have this quote, chaos when the present determines the future, but the approximate present does not approximately determine the future. That's another statement of extreme sensitivity to initial conditions. So it's deterministic, the present determines the future, but if I don't know the present just right, I will not be able to predict the future very well at all. And so that's chaos. And that relates to another popular saying, the butterfly effect. Some people misquote the butterfly effect and say that it represents like a butterfly flaps its wings in Africa and that somehow causes a storm somewhere else. That's not what the butterfly effect is saying. That would imply like a causal link between like a butterfly and a storm. What it's actually saying is that in a universe where the butterfly's wings is up, you'll get a very different world than a universe where the butterfly's wings are down. It's extreme sensitivity to initial conditions. It's not that in this universe, the butterfly flaps and that causes like a chain reaction. That's just fantasy. What it's saying is if you're modeling, if you're doing a digital twin of the whole world, you better get the butterfly's wings correct, because if it's up, then a certain set of events might happen because it's going to obscure, like, it's going to prevent certain things from happening or whatever. But if the wings are down, another set of events might happen. And so it's a nonlinear causality. It's not about the flapping of the wings. It's about getting the initial conditions right. In most systems, whether the butterfly's wings are up or down isn't going to matter because it's been buffered by all the other behavior in the system. But in chaotic systems, every little detail matters. Like Ian with the water, if it hits the hand in a slightly different way, you get a very different response. All right, so questions about chaos. To clear how that differs from randomness. All right. Well, so looking forward, like I said, keep working on your projects. We've got an open lab on Tuesday. Very happy to help. Muddiest Point due Sunday. I got you feedback back on all of your check-in assignments, so please take a look at those. Like I said, open lab next week, and then the last week of class, we're going to have Tuesday after Thanksgiving, final exam review. On Wednesday night, upload your presentation videos and final reports. There's no real grace period there. After they all get uploaded, then we'll randomly assign the peer reviews. And we want to make sure everybody's got Thursday, Friday, and Saturday to have time to do the peer reviews. Then we'll do stage 1 on Thursday. The peer reviews will be due Saturday. We'll have a final Muddiest Point on Sunday, and then stage 2 during finals week. So any questions about the schedule moving forward? Okay. All right, so let's do what is, I think, our final attendance exercise, because I won't take attendance on Tuesday. Let me just get centered here again. And so I'll put the link in the chat for convenience. And so I guess my question is here, so if you don't get this right, that's fine. But it's just, it has to be coherent. The word stochastic is from a Greek word for what? So I was saying that stochastic is Greek for if I used one word or another word. So stochastic is not a synonym for randomness. Stochastic actually has nothing to do with randomness in direct translation. So what word does it come from, or what concept from Greek does stochastic come from? And that's all I've got for you. So if you have any other questions, feel free to come up. Otherwise, have a good weekend. And if you don't come in Tuesday, have a good holiday. Any questions online? If not, I'll stop the recording.